Welcome to qnawire.
So in this video, we're going to work through question 114 from chapter 20, which says sodium tripolyphosphate, or Na5P3O10, is used in many synthetic detergents. Its major effect is to soften the water by complexing Mg2+ and Ca2+ ions. It also increases the efficiency of surfactants, or wetting agents, to lower a liquid's surface tension. The pK value for the formation of MgP3O10 3- is negative 8.60. The reaction is Mg2 plus P3O10 5- yields MgP3O10 3-. Calculate the concentration of Mg2 plus in a solution that was originally 50 milligrams per liter after 40 grams of Na5P3O10 is added to 1 liter of the solution. So let's start out by calculating our starting concentrations in units of molarity so that we can put them into an icebox. So we know our concentration of magnesium ions is 50 milligrams per liter. So we can convert milligrams to grams and then grams to moles using the molar mass, which is 24.31 grams per mole. And we end up with 0.002057 moles per liter. Our concentration of P3O10 is 40 grams per liter, and the molar mass of P3O10 is 252.91 grams per mole. So we divide by the molar mass, and we get 0.1581 moles per liter. And then the other thing we have, the other information we're given is the pK value for the formation of our complex ion. And we're told that that pK value is negative 8.6. So remember that a very small pK value corresponds to a very large equilibrium constant. So our equilibrium constant is 10 to the negative pK, or 10 to the positive 8.6. which gives us 3.98 times 10 to the 8th, which is a very large equilibrium constant. So what does that say about our reaction? That says that we're going to have mostly products at the end when we reach equilibrium. So let's set up an icebox. So initially, we have our 0.002 moles of Mg2+, our 0.15 moles of P3O10, and no moles per liter of our MgP3O10 complex ion. And then we know that our equilibrium constant is very large, so whatever our limiting reactant is, whichever reactant we have less of, we're going to use more of that. We're going to use all of that. So in that case, that's our magnesium ion. So we're going to subtract 0.002 moles. And then for every 1 mole of magnesium that reacts, we also react with 1 mole of P3O10. So I'm also going to subtract 0.002 moles here. And then for every 1 mole of Mg2+ that reacts, we form 1 mole of MgP3O10. So I'm going to add 0.002 moles over here. Then you would think that this would evaluate to 0, and it's definitely going to evaluate to a number very small that's close to 0 because of the size of our equilibrium constant, but we want to calculate its exact value. So this is our x value, our unknown. And then once we do the calculation in our P3O10 column, we end up with 0.1560 moles per liter. And we have 0.002 moles per liter of our MgP3O10. So let's plug these into our expression for our equilibrium constant. So the equilibrium constant is equal to products divided by reactants raised to their stoichiometric coefficients. So that's MgP3O10 divided by Mg times P3O10. So we end up with 3.98 times 10 to the 8, that's our equilibrium constant, is equal to 0.002057 molar, that's our MgP3O10, divided by 0.1560, that's our P3O10, and X is our magnesium. So then we just solve this equation for X, and it ends up being by dividing both sides by 3.98 times 10 to the 8 and multiplying both sides by X. And that's going to evaluate to 3.31 times 10 to the negative 11 molar. So that's our final concentration of magnesium ions.